Here's a little experiment to show polarization of electromagnetic waves. Polarizers are, again, a whole series of aligned molecules. So if I hold this up to the window, you can see it's blocking out some of the light, but it doesn't make any difference, and which way I hold it. But if I put two together, well, I can completely block out the light. That's because the light from the sky is actually not vibrating in all directions, but only in some. And if it gets to pass through the gaps in the filter, then what happens is it gets through. If the filter's the wrong direction, then it'll cancel them out. It'll change what you see about the sky. But actually having two filters next to each other, what they do is they can actually be used to cancel out signals. We use this quite a lot in communications to not let different radio and TV signals get mixed up. Mobile phone signals. So what I'm going to do is I'm going to just take an electronic sensor, okay, so a light sensor here, and I'll stick a polarizing filter in front of it. Over here you can see the amount of light passing and reaching the filter. When my hand's in the way, strangely enough, not much of it. If I block some out, it doesn't go to zero because it's still light in the room, so it's not going to be perfect readings, but we will see and be able to take readings from this. And when I put filters in front of each other, then it can either go down to very low numbers or it can go much higher. So it all depends on the actual thing itself. So what we're going to do is I'm going to take some readings and tell you the angles that these are at. So for example, this is at, with my protractor up there, 0 degrees roughly. And what I'd like you to do is plot the actual amplitude, the maximum reading of light, i.e. what it says on the dial over here, against the angle itself. So 0 degrees gives us that, so 530. Okay, you might want to round it up to near as 10, I suppose. That one is at 20 degrees. That is at 30 degrees. That is at 40 degrees. Let me just make sure it's there. There we go. 50 degrees. 60 degrees. You can start to see that the much less is getting through. 70 degrees. That's about 80 degrees, a bit hard to tell. And then completely square is at 90 degrees. Okay, so if you take those readings and plot them against the angle, what you might find, you should find, is what Malus found many years ago, so came up with Malus Law, in that it appears to be to do with the sine of the angle. So your curve that you'll get on your graph should give you some sort of sine wave. So you can verify whether that's true or not. But it gives us this idea of how much polarizing filters cut things out. And the clever thing is that we can actually use it as well to start thinking about other changes, so we can examine things in the middle. So if I hold up two filters and I put some other material within the middle of it, then I can actually get readings about that. And it tells me about the structure in the material in the middle as well.